Hello everybody. We start our next lecture. And today I would like to start with a corollary of the last theorem. Okay. And to formulate, I will start with general definition. If there are n functions let's say phi j of x, j from 1 up to n, with the domain D in, let's say, Rm, then we call let me write it phi, which maps D to Rn, phi of x equals to phi 1 of x, so on up to phi n of x, a mapping from D to Rn. Sorry, Rn here. So what we had in theorem 2 was a mapping, an example of a mapping, and we had a mapping from Rn plus m into Rn. And now wait a minute, one more. If functions phi j from 1 up to n are differentiable, maybe continuously differentiable, then phi is called differentiable. Or continuously differentiable, respectively. Continuously differentiable. Mapping. And now I can formulate the theorem, theorem 3, inverse mapping theorem. If phi is defined on a neighborhood of x naught in Rn, phi u of neighborhood into Rn, maps to Rn. And phi is continuously differentiable. On the neighborhood, and also with the Jacobian d phi 1 so on phi n over x1 so on xn at x naught not equal to 0. Then there exists an inverse mapping psi, which is defined in a neighborhood of y naught equals to capital phi of x naught, and continuously differentiable. There, I mean in that neighborhood. Okay. Proof. And the proof is very easy. We just refer to Theorem 2. So consider such a set of functions for fj of x, y. We'll define it as follows. So just functions phi j of x minus yj, j from 1 up to n. And that is the definition of our functions. So we take the original functions, which are components of our phi stone, and form such difference. Then what happens? Look, so you see, fj, in fact, where they are defined? They are defined on our neighborhood of the point x naught times Rn, because of course for yj we have no problem to define, right? Because just numbers, we subtract numbers yj and nothing else. And yeah, So functions fj are defined, and then what we do? We check that, and they satisfy all conditions of theorem 2. Why? Because, look, what we know, fj at x0, y0, what is it? These are phi j of x0 minus y j, sorry, wrote like that, right? Jth coordinate of the point y0, and look at the definition of y0. Y0 was the image of the point x0, so that is 0 by definition. 0 by definition. And also, what is about, the Jacobian? And here, what's important, that we want to apply theorem 2, but now with different role of variables, x and y. What I want to say. In theorem 2, we checked the Jacobian of our system of functions fj with respect to variables y's. And we wanted to solve the system with respect to variables y's. But now that is not a problem. Look at the form of our function. Yeah, look. So no problem to express y as a function of x, right? They are given. If we write equals to 0, then yj equals to phi j, right? We don't need to solve this system of equations. I mean, when we write fj are equal to 0 with respect to variables yj. We want to solve it with respect to variables x. It means that we need to check the Jacobian with respect to variables x. And what is this Jacobian? We need to consider partial derivatives of our functions with respect to variables x. But that is the same as to take partial derivatives of functions phi j. Because, okay, if we differentiate with respect to x's, yj give us zeros after differentiating. Hence, this Jacobian coincides with the Jacobian of the system of functions of phi j, and that is not 0 by our supposition at x0. So at x0, that is not 0. Hence, and of course differentiability and so on, everything is satisfied. Hence, we can apply. So by applying theorem 2, what we have? For arbitrary epsilon 1 and so on, epsilon n positive, there exists delta positive such that for all y in the we denoted it k delta y naught. Yeah. For all y in the what we had, so we wanted to solve with respect to variables x equals for all y's here. There exists a set of functions. They exist functions psi j of y1 so on yn, such that the system of equations psi j of y1 so on yn equals to xj, j from 1 up to n, and fj of x 1 so on xn y1 so on yn equals to 0, j from 1 up to n are equivalent for all xy which belong to, so as I said, the row are changed. So first I should write product of intervals x j naught minus epsilon j x j naught plus epsilon j times our cube and dimensional cube with center at y naught. So roles are changed. So that is just by applying theorem 2. So we want to solve the system, that is the system of equations, this system of equations. We want to solve it with respect to variables x. So we want to write variables x as functions of y's. But in theorem 2, we wanted to write y's as functions of x. That is the difference with theorem 2. But then look carefully at what is written now. So it means that, what is this system? This system is yj's are phi j of x. So that is equivalent to say that the vector y is phi of x. So you see, y equals to phi of x is equivalent to, if I collect all functions psi together, then it means we have x equals to psi of y, where the mapping psi is given by functions psi j. And what is it? You see, y equals to phi of x is equivalent to x equals to psi of y. It means that psi is inverse mapping. Inverse mapping. But of course, that is valid only in such a set, but it's enough for us because this cube contains a neighborhood of y naught. Hence, we constructed the inverse mapping. And also, last assertion about continuously differentiable. Again, it follows from Theorem 2, because in Theorem 2 we deduce that functions psi j are continuously differentiable. And hence, according to the definition, our mapping is continuously differentiable. So, theorem is proved. Theorem is proved. And now how to compute derivatives of that inverse mapping. So, let me write remark. To compute, remark 1, to compute partial derivatives of functions psi j's apply the rule to find partial derivatives in Theorem 2. That is what I did after the proof. So when we proved Theorem 2, after that I wrote to you how to compute with the help of the Jacobian matrix. And it was written that to find partial derivatives, so d psi 1 over dy 1 this matrix, what we need to multiply the inverse to the Jacobian matrix, that is and we need to multiply to the matrix which consists of partial derivatives of those functions with respect to variables y. And to put minus here, to put minus. Why I don't write minus here? Because look, what are partial derivatives? Let me write it here. What they are? Look, here are our functions. We differentiate with respect to variables y's. You see, if we differentiate function fj with respect to variable yj, what we obtain? Derivative with respect to y, what is it? -1, of course. So that is -1 if I equals to j, and if they are different, then no yj, right? So zeros if I not equals to j. So it means the matrix which consists of those partial derivatives is minus unity matrix, right? And here was minus, so minus disappears, right? And if we multiply a matrix to a unit matrix, we have the matrix itself, right? So I don't need to write anything else. So that is how to compute, you see. How to compute partial derivatives of an inverse mapping. With the help of the Jacobian matrix, just take the inverse to the Jacobian matrix of our original not the Jacobian, because Jacobian is a number, but Jacobian matrix, which consists of partial derivative of functions phi j's. Okay. Remark 2, maybe I wrote it also here. Theorem 3 asserts the local invertibility the local, that's important. We cannot guarantee the global invertibility. Why? Example. Consider the following mapping, just polar coordinates. Polar coordinates, right? You see, that is a mapping which maps, okay, r varies from 0 to plus infinity, and phi, okay, phi in R or in R to R2, right? To R2 without 0, in fact, without 0, 0, without the origin, And what is about the Jacobian? So dxy with respect to r phi. If we compute, what is it? So if we differentiate, let's say, first function x, so cosine phi, then minus r sine phi. Here we have sine phi r cosine phi. And if we substitute, the determinant equals to just r, which is not 0 if r belongs to 0 infinity. So that is not 0, right? But nevertheless, there is no inverse globally. Why? Because points, let's say, r phi and r phi plus 2 phi, they have the same image, right? The same point. They are mapped into the same point. Hence, globally, this mapping has no inverse. So you see, the Jacobian is never 0, right? So we can find the locally, only locally we can find an inverse mapping. But we cannot find the inverse globally. So there is no inverse mapping, right? In general. Only locally. near a point. So if we, for example, if we consider instead of r here, if we consider, let's say, interval, small interval of the length smaller than 2 pi, then we can define the inverse mapping, because there will be no such a possibility to obtain the same image for two different points. Okay. Okay, so that is for inverse implicit functions theorems. So the section is over now, and we'll apply it a little bit later, and of course the inverse mapping theorem and also implicit mapping theorem, implicit function theorem, all of them are heavily used for theoretical purposes in many areas, in fact, of mathematics. But okay, now next section, and number is 5. Section 5. Extrema of functions of several variables. So let me start with definition. A point x0 is called a local minimum point for f of x if there exists a neighborhood u of x0 such that f of x greater or equal than f of x0 for all x in our neighborhood. Analogously, a local maximum point x0 is such that for all x in a neighborhood of x0, we have f of x less or equal than f of x0. And yeah, if inequalities inequalities are strict for x in neighborhood without, so in a deleted neighborhood, right? In a deleted neighborhood, then x naught is a point of strict local minimum or maximum. Minimum or maximum. And of course, like for functions one variable, we call it in any case x naught is an extremum point. So quite often the word local will be omitted, but in general you should remember that we are talking only about local extremum, not about global one. Okay, so now I'll formulate theorem 1, which is necessary condition of local extrema. So if f is differentiable at x naught and x naught is an extremum point, of f, then partial derivatives at this point are equal to 0 for all possible variables. So let me recall that we consider functions of n variables. Okay, let's have a break. Yeah, there is a question about point x naught, and okay, maybe I should indicate it explicitly. So x naught is a point in Rn. So this is n-dimensional point. Like everywhere here and in former section also when we discussed. Okay, proof. So fix a number of variable I from 1 up to n and put xj equals to x naught jth coordinate for j from 1 up to n and j not equals to I. So we fix all coordinates of our vectors to be the same as coordinates of x naught. So let me recall that x naught is the point with once again I forget how we wrote before. Oh, I think it was in inverse order, right? Yeah, it was like that. X naught equals to x1 naught, so on, xn naught. I'm always mixed with this where to put 0. Doesn't matter. Okay, let it be like that. So our point x naught has n coordinates like that, and we fix all coordinates should coincide with coordinates of x naught except for only one. Then what happens? Then by the definitions in fact, I mean both definitions of extrema of functions of several variables and of one variable altogether, and also by differentiability and partial derivatives. So by definitions, what we have? The function f of x1 naught, so on I minus 1 naught xi, xi plus 1 naught, so on xn naught, so I fix everything, is a function of one variable xi, which is differentiable at xi naught, and xi naught is an extremum point, is its extremum point, So why? Because look, so for example, consider the case of maximum. Yeah, so you see, this is the inequality for maximum, f of x less or equal than f of x naught, right? For arbitrary point x in the neighborhood, right? So now what we do, we fix all coordinates to be same as in x naught except for one coordinate. One coordinate vary. Then for sufficiently small, for sufficiently close to xi naught, right? If xi is sufficiently close to xi naught, then this point is in a neighborhood, u of x naught, right? Hence our function will be less or equal than f at x naught. So indeed we have the extremum, the maximum in our case for our function. So then what happens? Fermat theorem that is from the first semester, necessary condition of local extremum for one variable, says that the derivative of that function should be 0. And what is the derivative? If all variables are fixed, then the derivative is just partial derivative. Okay, let me write. The derivative dxi of that function of one variable should be 0. That is a function of only one variable, and I take this derivative when xi equals to xi 0. That should be 0. And that is equivalent, if we differentiate such a function, then that's equivalent that we consider partial derivative of function f with respect to variable xi at the point x naught, and it is 0. So I was arbitrary number of variable, hence the theorem is proved. The theorem is proved. And let me write a remark. The condition that all partial derivatives are equal to 0, I from 1 up to n, is equivalent to say that the differential of our function at x naught is identically 0. Why this is true? Because what is differential? Differential is a linear function with respect to variables dx1 so on dxn with coefficients partial derivatives. So partial derivatives are zeros, hence the differential is 0. Right? Okay. And also let me give one more definition. If df at x naught equals to 0, then x naught is called a critical point. Critical point of f. So critical point is a point where differential is 0. So that is quite analogous to the situation with functions of one variable. Let me recall. So Fermat's theorem says that if function has an extremum, then derivative is 0, right? And point where derivatives are zeros were called critical points. And here it's the same, but instead of one derivative, we should consider either all of them together, they should be 0 simultaneously, or what is equivalent, we can say about differential, and that is more convenient, in fact, to talk about differential. Okay, now what happens for sufficient condition? I mean, of course, a critical point need not to be a point of extremum. So let me give an example. Consider function f of x, y of two variables, x power 4 minus y power 4. So that is a function of two variables, and if we compute partial derivatives, so df with respect to x is 4x cubed, and that is 0 implies x equals to 0, and analogously, if we consider partial derivative with respect to y, that is minus 4y cubed, and that is 0 implies y equals to 0. So 0, 0 is a critical point. Of f. But that is not an extremum point. Why? Because you see 0, 0 is not an extremum point. Of f. Why? Although, even you see, in this case, that is an extremum point in each of variables. Why? Because if we consider f of x0, that is just x power 4, right? So has minimum at x equals to 0. But f of 0y equals to minus y power 4 has maximum at y equals to 0, right? So you see, in one variable we have minimum, in other variable we have maximum. So it means that we can find as close to the origin as we want points where our function is either positive or negative. So we have no extremum at the origin for that function. So this example shows that the situation now may be essentially more complicated than for functions of one variable. Nevertheless, we can give an answer to the question how to determine if we have a local extremum. And that is Theorem 2. Sufficient condition of local extremum. If f is twice differentiable, okay, let me suppose even more, in a neighborhood of x naught, and x naught is a critical point of f, then first, if second differential at the point x naught is a positive definite quadratic form in dx1 so on dxn, then x naught is a point of minimum. Let me emphasize of local minimum of f. If second differential is a negative definite quadratic form in dx1 so on dxn, then x naught is a point of local maximum of f. That is like we had for functions of one variable. For functions of one variable, if second derivative is positive, then we have minimum. If second derivative is negative, we have maximum. Here analogously, but now we should talk about second differential, because we have many second derivatives, partial derivatives. But the third assertion is we had an analog for the case if so if second derivative is 0, but let's say third derivative is not 0, then no extremum. There was such a condition. And something similar is if second differential is an indefinite quadratic form. Okay, I will not repeat in dx1 so on in dxn. Then x naught is not an extremum, a local extremum point. Point of okay, proof. So f satisfies Taylor's theorem about Taylor formula with piano remainder. So because twice differentiable, hence we can write f of x equals to f at x naught plus first differential at x naught plus second differential divided by 2, factorial doesn't matter, either to write down factorial or not, plus little o of norm x minus x naught squared as x minus x naught tends to 0, and where dxj are equal to x minus xj minus x of, I forget how, xj naught, j from 1 up to n. So I recalled Taylor formula with Peano remainder. We just substitute our differentials. Okay, that is in general, but we know that x naught is a critical point. And what means x naught is critical point? X naught is critical point means that the differential is identically 0. Differential is 0 by the definition of the critical point. So we can write f of x minus f at x naught equals to second differential. Oh, here I forget x naught. At x naught 2 factorial plus little o of x minus x naught squared. Okay. Now, let me recall what is second differential. So the second differential is the following object. That is the sum j from 1 up to n, partial derivative with respect to xj, times, instead of differential, I'll substitute xj minus xj naught. So we take square and then substitute our function f at x naught. That is what is second differential. What is second differential? Now, if we divide this expression by the norm of the vector in square, then what we have will obtain, okay, I'll put it here like that. So xj minus xj naught, but now without square because square is here. Okay. So now what is written here? Let me denote Tj to be xj minus xj naught over the length. Oh, sorry. Here, I'm sorry. Here is the length of the vector. So x minus x naught vector. That is Tj. So I divide it by this number and I put it everywhere. J from 1 up to n. J from 1 up to n. Then what is written? Then here what is written is the following thing. So let me write it in details now. Okay, I will write in details like that. The sum j from 1 up to n, sum k from 1 up to n. So we take square. To take square, we need to consider all possible products of those terms, and it gives us second derivatives with respect to xj with respect to xk. Then I substitute f at x naught times those quantities which are denoted by t, so tj, tk, all possible products. So that is the second differential, which I wrote. So I wrote this second differential divided by this thing as a quadratic form, And we know that the sum of tj's squared, so if we consider t1 squared plus so on plus tn squared, then what is it? We take squares, right? And here square of the length. But sum of squares of components is precisely square of the length. Because what is the length of a vector? Square root of sum of squares. So it means that is 1. That is quite important. Why? Because look, that is a unit sphere in Rn, bounded closed set. Bounded closed set. Hence, this is a compact. Hence, this is compact set. Compact set. So now, let me denote it by, let's say, capital F of t1, so on, tn. So we have a function of n variables, capital F of t1, so on, tn, right? Then what happens? Look, these are fixed numbers, right? Partial derivatives, fixed numbers, and we have n variables. But obviously this is a continuous function of t. So continuous function, because that is a polynomial of degree 2 in variables t1, so on, tn. So that is a continuous function. Continuous on compact set t1 squared plus so on plus tn squared equals to 1. And hence it has maximum and minimum, right? Hence f attains maximum and minimum on this set. Now look, for example, proof 1. So for 1 we have positive definite quadratic form, right? Positive definite. Then what we know, capital F is positive for all those values, right? Because what is positive definite? It is positive everywhere except identically zeros, right? So what is positive definite quadratic form? Positive definite quadratic form means that once at least one of them is not 0, then this is positive. The only case when it is 0 is when all of them are zeros, right? That is positive definite. And of course, it is not possible that all of them are zeros for the unit sphere, right? Because, of course, one or more can be zeros, right? But at least one should be not zero. So it means everywhere it should be positive, right? But then, because of that, what follows? So you see, everywhere is positive, and the function attains its minimum, right? Hence, the minimum is also positive. So it means that there exists a positive quantity m, which is minimum in fact, right? Such that for all q1 so on tn, in our, let me denote it by S, sphere S. In S, right? For all points in S, we have capital F of q1 so on tn is greater or equal than m. And that is quite important, that now we have a boundary below. Then let me return to our representation, let me call it star, representation for the difference, right? So, if I return, so star implies that f of x minus f of x naught divided by x minus x naught equals to the second differential, 2 factorial also x minus x naught squared plus little o of, look, so if I divide it by x minus x naught squared, then I divide by this and I obtain little o of 1, right? Now look, what we know. You see, that is our quadratic form, capital F, which is greater or equal than m. So this quantity greater or equal than m, always, right? And this tends to 0. So it means that altogether that is greater or equal than m over 2 in a neighborhood of x naught. So this tends to 0, that is greater or equal than some positive number. Hence, for sufficiently small x minus x naught, that is greater or equal than m over 2. So what it means, let me rewrite now. So I'll multiply here squared. I'll multiply back that inequality. So what it means? F of x minus f of x naught is greater or equal than m over 2 times x minus x naught squared in a neighborhood, right? But in particular, what it means? F of x, that is non-negative number, right? So f of x greater or equal than f of x naught. So we have local minimum. And analogously, second assertion is proved. Completely analogously. So for the third, what we need. Third, you see, if we have indefinite form, then what it means? Indefinite form. Then we can find values of t, right, such that this quadratic form has either positive or negative values. So what means indefinite quadratic form? It may be positive, may be negative, right? But once again, if we proceed like here, so if this is positive, so it means we multiply by that one and we obtain, you see, that can be as small as we want, right? So the point will be very close to x naught, but the right hand side will be positive, or it will be negative. So this difference has either positive or negative signs, as close to x naught as we want. So quite analogously, but we need to consider, yeah, so once again, choose yeah, I think it's better to write down the proof of third part explicitly, and I'll do it next time, yeah, because now time is practically over. Yeah, I think I should better to write it down explicitly. So second part is proved analogously to the first one. Third part I'll complete the proof next time. Okay, thanks for your attention then.